In this video, we will take a look at this concept of Credit Valuation Adjustment, CVA, when it is applied to a very special but still a rather simple position, which is that of a European option. Specifically, in this video, we will take a look at this solved example from reading 12 of book 2 of the FRM part 2 curriculum. Okay? As per this solved example, it's given to us that we have purchased, let's say, a 2-year uncollateralized option, which can be, let's say, a European call option from a company, from a counterparty, and using the Black-Scholes-Merton model, the price of this 2-year uncollateralized option has been obtained to be $3. Okay? Also, it's given to us that there is, let's say, a 2-year zero-coupon bond which has been issued by the same company from whom we have bought this option, and this zero-coupon bond has a yield which is 1.5% greater than the risk-free rate. Okay? The task at hand is to find the value of this option after duly taking into account the default risk of this company from whom we have purchased this option. Okay? So, the value of my option after taking default risk into account, let it be denoted by V risky. This V risky can be written down to be equal to the value of this option without taking into account the default risk of my counterparty, denoted as VND, where ND stands for non-default, that minus this adjustment called CVA. Okay? As per the information given to us, this VND is nothing but the price or value of this option calculated using the Black-Scholes-Merton model, which is $3. Okay? So this VND, let's note it down, is equal to $3. Now, coming on to this adjustment, which is CVA, I need to interpret this adjustment to be the present value of the expected cost that I will incur if my counterparty were to default. Okay? To calculate CVA, what I need to do is that I need to break down this 2-year period, which is the life of my option, into a number of thin time slices. Okay, let the number of time slices be m, and for each time slice then I calculate the product of the discounted expected exposure, denoted by lowercase v, this times the loss given default, denoted by 1 minus r, where r is my recovery rate, this times the marginal probability of default for the given time slice. Okay, so we calculate the product of these 3 inputs for each time slice, and then we sum over this product for all the time slices that we have. That will give us our CVA. Okay, now to calculate CVA, let's first and foremost focus on this important input, and this is V sub I. Okay, this input is essentially the discounted expected exposure for a given time slice. Now, to arrive at what this V sub I should be, let's do this. Let's, for reasoning's sake, shift away from the chosen model which we have here, which is the Black-Scholes model, and instead, let's say, think of the binomial tree model. Okay? Now, this is, let's say, how my binomial tree will look like. Let's say it has many more steps, and I have only shown you the first 3 steps here. Okay? Let's assume that the time step of this binomial tree has been chosen in such a way so that the time slices which have been created in this tree exactly match with the time slices which I am using for the purpose of CVA calculation. Okay? For this binomial tree which I have shown here, which only has these 3 time slices being shown, let us label these 3 time slices. The first one is the time slice corresponding to I is equal to 1. The second one corresponds to I is equal to 2. And the third one corresponds to I is equal to 3. Okay. Now, how does this binomial tree model work? Essentially, on the last time slice, all the nodes that I will have on that time slice, the value of my option on those nodes will just be equal to the payoff which my option has to offer. Okay, so we will populate the value of the option as of the last time slice to be equal to the payoff which the option has to offer. Then, sequentially, one time step at a time, we fold back this binomial tree to finally arrive at the value of the option as of this node, which is the value of my option as of today, right? Let me assume that the final value of the option, the VND, which comes from this binomial tree, exactly matches the value which we have from the Black-Scholes-Merton model, and that is $3. Okay? Now let's say I have to find the discounted expected exposure, which is my lowercase v, for this time slice. Okay, the time slice for which I is equal to 2. For this purpose, let me assume that I have one step at a time folded back my binomial tree, and let's say I am at this time slice and I have found the value of my option on each of these 3 nodes of my time slice. Okay? Now, if I am positioned as of today, the value that my option will take as of this time slice is a random variable, right? It will depend on which of these 3 nodes I will land at. Let me denote this random variable by a capital V with 2 in the subscript, which denotes that this is the value of my option corresponding to the second time slice. And as I have just now said, standing as of today, this V2 is a random variable. Okay? Now, based on this future value of my option as of this second time slice, I can define the exposure for this time slice to be simply equal to E2, which is my exposure for this time slice, is max of or higher of V2, the value of my option as of this time, comma 0. Okay, it's telling me that only when the value of my position, the value of my option in this case is greater than 0, is positive, will I have an exposure to my counterparty. Okay. Now, since in this situation we are working with a position which cannot have a negative value because we are dealing with the European option in this situation, therefore, we needn't do max of V2, 0 because V2 cannot be negative, right? So, therefore, in this situation, my exposure E2 is simply equal to V2, right? Now, to arrive at lowercase v, my discounted expected exposure for this time slice, all I have to do is I have to find the expected exposure, which in this case is nothing but the expected future value of my option as of this time slice and discount it to today. That will give me my lowercase v for this time slice. Okay. Now, if you find the expected value of my option as of this time point, which is nothing but the probability weighted average of the value which my option is allowed to take as of this time point and discount it to today, it's nothing but folding back this binomial tree in one shot from this time slice to what we have as of today, to the node as of today. Okay, it basically amounts to folding back my binomial tree in one shot and not sequentially one time step at a time. Okay. Now remember this, that if you are dealing with a position in which we do not have any intermediate cash flows, and also if we do not have any early exercise to worry about, Sequentially folding back your binomial tree one time step at a time gives you the same result as folding back your binomial tree in one shot. Okay, so folding back your tree in one shot from this time slice to today will give you the same result as what you get from folding this tree one time step at a time. Okay, and therefore we can reason this out that the discounted expected exposure for this position that we are working with is nothing but the value of my option as of today, the VND as of today. Okay, so this is the essence of this particular solved example, and that is for this very special, very simple position, the discounted expected exposure for any time slice is equal to the fair value of the option as of today. Okay, if you've understood this bit, this solved example becomes very, very simple. Okay, if this were to be true, it simplifies my CVA calculation quite a lot, because this guy becomes independent of I, and this guy along with 1 minus R can be taken out of my summation. And therefore, for this situation, my V risky becomes equal to my VND minus my CVA, which simplifies as VND times 1 minus R. Okay, these guys have been taken out of the summation. This times the sum of the marginal probabilities of default for all the different time slices. Okay, this sum is nothing but the total unconditional probability of default of my counterparty during this period of 2 years. Okay, next, this logic which we've just now outlined for this risky option position can be actually repeated for the zero coupon bond issued by the same company as well. And this will give us a very similar looking equation for the risky zero coupon bond as well. And this equation would look something like this. The value of my risky zero coupon bond, taking into account the default of my company, my counterparty, is equal to the value of my zero coupon bond ignoring the default of my counterparty minus this same value times 1 minus R times the total unconditional probability of my counterparty defaulting. Okay, look at these two equations, and in these two equations, if I were to respectively for each equation take this guy common, and then on the left hand side it will give me this equality that V risky over VND is equal to B risky over BND. Both of these are simply equal to 1 minus R times the total probability of default. Okay, now this guy can be easily calculated. B risky, which is the value of my zero coupon bond taking the default risk of my company into account, would simply be equal to the face value of this ZCB, which I can assume to be 1, times a discount factor which works with, let's say, a risky yield as the discount rate. Okay, so 1 times e to the power minus y, which is like a risky discount rate or risky yield, times the time, which in this case is 2 years. Okay, then the value of my zero coupon bond without taking into account the default risk of my company would simply be equal to face value, again $1, times this time a discount factor which works with a risk-free discount rate, okay, a risk-free yield, right? This gives me then a very simple equation to calculate my V risky. My V risky is simply equal to VND times e to the power minus YND times 2 years. And this difference between the risky and the risk-free yields, the credit spread, is already given to us to be 1.5%. Okay, this guy we know is $3, this guy we know is 1.5%, and this then gives me that V risky is equal to, you can check this, $2.91. Okay, this tells me therefore that the CVA for this particular option position is simply equal to $3 minus 2.91, which gives me a CVA of 9 cents. Okay? This video is all about understanding this concept of CVA, Credit Valuation Adjustment, when applied to this very simple position of a European option.